The van der Pol oscillator is a nonlinear oscillator that has a damping term that is proportional to the velocity of the oscillating mass. It's a second-order differential equation, therefore we cannot use directly the Euler method, we'll have to adapt it. But let's see how this adaptation works. We have seen that the differential equation for the van der Pol oscillator is second order. The reason why it is second order is because it involves the second derivative of the position of the oscillator. We're going to assume that the mass of the oscillator is 1, and we have here on the right-hand side two terms. The first term is a damping term, which is proportional to the momentum. Mu is a constant that controls this damping effect. When mu is equal to 0, the equation becomes that of the harmonic oscillator. Since it is second order, it has to be supplemented with two initial conditions. We're going to give an initial condition for the position and also for the momentum. The goal is to integrate this ODE in the interval t0 plus capital T. We'll do that in n steps of size delta t equal t over n. The earlier method was valid for first order equations. However, this is second order. In order to transform this equation into first order equations, we're going to define the momentum as a new variable. Notice that if we take the derivative of the momentum with respect to time, we get the second derivative of the position with respect to time, which is the quantity that appears on the left-hand side here. The first thing we're going to do is to divide the integration interval into a grid of monitoring times that are equally spaced. Tn is equal to t0 plus n delta t, where n is an integer running from 0 up to capital N. We're going to monitor the trajectory in a two-dimensional space. Therefore, we're going to define xn as the position of the oscillator at time tn and pn as the momentum of the oscillator at time tn. Let's transform the second-order differential equation into a set of two first-order differential equations for the position. And for these, we'll use the definition of the momentum in reverse. And then another first-order equation for the momentum. Notice that these first-order differential equations are coupled. That means that the equation that gives us the derivative of the position with respect to time is a function of the momentum, and the derivative of the momentum with respect to time is a function of both the position and the momentum. Since they're first order, now these equations can be solved using the Euler method. The trajectory starts at x0, p0. Remember that we're monitoring the trajectory in a two-dimensional space of position and momentum. The value of the position at time tn plus 1 is given by this expression, xn plus pn times delta t. The value of the momentum at time tn plus 1 is the value of the momentum at time tn plus mu times 1 minus xn squared times pn minus xn times delta t. These two steps are repeated for n equals 0, 1, 2, up to n minus 1 to generate the whole trajectory. Let's simulate a trajectory of the van der Pol oscillator that starts close to 0. As you can see, initially it starts veering off from 0 and ends up falling into this cycle, which is a limit cycle. As you can see, the trajectory, which is not exactly doing the same thing every time it goes around, it basically follows this cycle very closely. If we had started the trajectory somewhere outside here, it would end up also following the limit cycle asymptotically. So we have seen that no matter where you start in the phase plane, that is the plane of position and momentum, you end up converging to this stable limit cycle, which is an orbit, a closed orbit for this nonlinear oscillator. Let's write the code for this simulation. This is the function Euler integration van der Pol, which we have used to integrate the trajectories of the van der Pol oscillator, starting at t0 at position x0 and momentum p0. Mu is the value of the damping parameter, t is the length of the integration interval, and n is the number of steps in which we have divided this integration interval. The first thing we do is to compute the size of the integration step, delta t, which is simply the length of the integration interval over the number of steps of integration. Then we compute the grid of monitoring times. LinSpace will compute a grid of equally spaced times between t0 and t0 plus capital T. There are n integration steps, that means that there are n plus 1 monitoring times. These two lines of code here serve to initialize the values of the trajectory and of the momentum. These are the initial conditions. The initial values of the trajectory are set to x0 for the position and to p0 for the momentum. We need two initial conditions because this is a second-order differential equation. And finally, this is the Euler integration method for the van der Pol oscillator.